Okay, let's start. So I think today we are going to see the last bit of theory, and then, as I told you, probably we are going to go back to the bacteria case. Probably I don't know if today at the end of the class or already tomorrow. And then tomorrow I will continue discussing the bacteria case with all the techniques that we know. And I want to show you also some of the things that we do, so you see how these kind of lattice models can be applied to experiments. I'm going to show you some experiments that we've been doing with bacteria growing in surfaces and microscope images, and how we try to model these patterns that form in the microscope with lattice models that are a little bit more cellular automata than the ones that we are studying, and the kind of spatial metrics that we can compute, correlation functions, and the biology that we learn. So tomorrow probably is going to be not very demanding in terms of focus. So in case today the night is long, I will not demand many neurons alive tomorrow. So yesterday we finished the class with this comparison, and we were discussing it a little bit. We were trying to understand why the mean field approximation, or the well-mixed approximation, remember the black line, was always overestimating the numerical simulations in the one-dimensional lattice. That was the red points. Remember, this was for the contact process, for which we wrote an equation for the density of occupied places that was this. And remember that basically the black line was after we said that spatial correlations don't matter, and therefore this Q0 conditional to plus was rho 0, that is 1 minus rho. And this gives us a very simple one-dimensional ODE. We calculated the fixed points, and that's what we got. And I told you that the key point here that was explaining this big discrepancy was this, of course, this approximation. And the idea that we were discussing is that we can try to write an equation for this Q0 plus. No? We can try to write an equation for the local density instead of the Q0 plus. Let's try to find a local density and write an equation for it. The way I'm going to introduce this is the way that to me is more intuitive, but in different books you will see it in different ways, and I'm going to tell you which is the alternative way and what is the difference, in case that at some point you go to some book and you find the different technique and the different steps, you can make the connection quickly. But it's not very hard. Great. So basically, the first thing that I'm going to do to try to improve my well-mixed approximation is I am going to, let me make space here. So this was well-mixed, already 1 minus rho plus. So the first thing I'm going to do is I'm going to write this conditional probability in terms of the density of pairs of nodes that are in the plus state. So imagine that I have a lattice, my one-dimensional lattice. And it has a given configuration. I am going to define this density of plus plus, this rho plus plus, as the density of pairs in this plus plus state. Okay? Instead of defining it as a conditional probability, I am defining it just as grabbing my lattice in pairs and seeing if they are in the same state. who can, actually I'm going to do it the other way. The way that I already learned works much better. I'm going to try to relate this rho plus plus to the quantities that I already know. So let's say I have rho 0 plus, which is the same as plus plus, but with a 0 and a plus, okay? Only 3 options. I'm going to say that rho 0 plus is equal to option A. This is going to be equal to Q plus 0 rho 0, or rho 0 plus is going to be equal to rho plus Q 0 plus, or rho 0 plus is going to be equal to rho plus Q plus 0, or option D, more than 1 from A, B, C is correct. Option E, known, is correct. 2 minutes or 3 to try to calculate rho 0 plus in terms of local probabilities and densities with paper and pencil. Is clear the exercise? I want you to write rho 0 plus in terms of a local density rho and a global density rho and a local probability Q conditional to something. Listening is good, but writing is better. Yes. Sorry? If they are the same thing? What do you think? They are? Okay. So then in your case, for instance, B and C would be correct, no? If B is correct, C is correct. It's a question. I already listened like a no back there. Few more seconds. You want until lunch to solve it? So raise your hand if you think that A is correct. We have 1 for A. Sorry? Sorry, Chris, I cannot hear you.
Could you just remind the order is the local probability?
Yes.
That
Q plus 0 means the probability that I take a plus conditional to having taken a 0 first.
okay, it can be any side, to left or right.
Yes.
Okay, thanks.
So, sorry, if you think that D is correct, then A and B are not correct, right? Just because the way I wrote the questions is not very clear. So if D is correct, keep your answer for D, okay? So who thinks A is correct? Who thinks B is correct? Who thinks C is correct? Everyone thinks something is correct. That's very good. Who thinks D is correct? D? E? Oh, if there is something correct, then E cannot be correct, no? Statement E is true, let's say. Who thinks the statement E is true? So let's try to calculate it. This is the probability that I take two neighbors randomly, and I take a 0 and a plus, right? So I can write this as the probability that I take a plus times the probability that I take a 0 condition that I took a plus. Right? So then the correct is number B. Sorry? Also A. Who agrees with that? Ah, good, good, good. Because this is equal to and I can use the symmetry of the pairs. Okay? Is this clear for everyone? Because it's going to be very important to understand that if I care only about taking pairs, I choose pairs. I divide as much as I only care about taking pluses. I look plus. The only thing that I'm doing now is I am defining my unit of choice to be a pair. Okay, this is different. This is a conditional probability. I take a 0 conditional to my previous choice that was a plus. Good. So I did the question for this because this is boring, no? Yes.
Sorry, I didn't get why A is correct.
You didn't get why is correct?
Why I didn't get why A is correct.
Okay. So what did I write? Row 0 plus, no?
Yeah.
Do you remember which option was A?
Q and row not. And row not.
This?
Yeah.
This is what I wrote in A.
Uh-huh.
So copy it. Try to solve it, and after lunch we discuss it. You have it? This is clear for everyone, right? Perfect. So, I'm going to rewrite my equation using this relationship. Everyone agrees? I am on purpose going to do a lot of changes between q plus 0, 1 minus q plus plus to make sure that you understand all the constraints. This doesn't mean that it is the most straightforward way of doing this. For instance, I rewrote q 0 plus as 1 minus q plus q plus conditional to plus because I want to use this expression here. If someone is going to tell me, Ricardo, could I write q0 plus in terms of row 0 plus and then use different relationships? Yes. The importance here is that I have two global densities and I have these local probabilities, and I have constraints. My constraints are right? So you can do the same as you do when you have a system of equations with two independent variables and you rewrite them in terms of whatever you want. Of course, depending on the problem that you want to solve, Sometimes it's more convenient to choose one or the other, because if you are interested, for instance, in looking at how the boundaries between the clusters move with time, then it is not very smart to choose rho++, because then you don't have information about rho++ immediately. You need to undo your change. So it's just as you do always when you have a system of equations with dependent variables, and you write it in terms of the variables that you want. Okay, all I'm going to do is that. I'm going to use, I have a set of variables, I have constraints, and I'm going to choose the variables that I want, and I'm going to write a system of equations. Okay? So now I can basically Q plus conditional to plus is equal to rho plus plus divided by rho plus, and I'm going to put this here. And I like writing it this way instead of writing an equation for Q plus plus, because my intuition is better thinking in terms of densities. My intuition. If your intuition is better thinking in terms of Qs, it's fine. Again, I'm just following what to me is easier to understand, and I hope then it's easier to explain, and then it's easier to communicate. But it's not the only way of doing that. Okay, it's the only time I'm going to repeat that. The last time I'm going to repeat that. Great. So now, because I didn't took this assumption, I have an equation for rho plus, and as we were discussing yesterday, it depends on rho plus plus. So what I need to do is I need to write an equation for rho plus plus. And this is where I need your neurons doing good connections. So don't be very disappointed if you are not really able to follow all the counting process that we are going to do now. It is usually not, I mean, well, maybe you are smarter than I. But it is not, at least to me, it never was something straightforward to think on how I create and destroy pairs. For nodes, yeah, it was easy. I put a plus, but for nodes, I don't know. In my opinion, you need a next level of abstraction that sometimes what requires is for you to sit down in front of the calculation and try to do it. I mean, it's just a matter of practicing. The more you practice, the better you will get. Okay, but I just want you to follow what I'm saying, and if you don't, tell me, and we will go back. Okay? So it says happy face even. So what are the processes that lead me to changes in rho plus plus? How can I, the idea is, how can I create and destroy these duplets, these pairs? And that's a question for you. Anyone has a suggestion for the first one? The first one is easy. Well, depending if you, death of one of the individuals, right? I have a configuration like this, and one of them dies. Remember that I am using delta equal to 1. I'm rescaling time still. So this would be minus rho plus plus. Question, yes.
Sorry, I got stuck thinking about why is Q plus plus the same as rho plus plus over rho plus?
Yes, but that is your previous question, right? Why is rho plus plus equal to?
Q plus plus times Q times rho plus, right? Yeah, this is.
What is the probability that I take two neighbors? If I choose simultaneously two nodes, the probability that they are in the plus state is equal to the probability that I first take one, and then times the probability that conditional to this choice, the next one is also plus.
Got it. Thanks.
Okay, so who agrees with this? This is the first reaction we always get. Remember, I am counting the pairs. So a pair will die, but I am missing something. What am I missing? Sorry? Over 2 or times 2? Who thinks it's over 2? Times 2? Why? Because it's the same. If this guy dies, so this guy dies. So which is related to your point, the process at which I destroy pairs, I know it's intuitive. It's not very intuitive, and that's why I want to start with this, is proportional to the number of pairs that I have, because if I only have one individual in plus, but I don't have a pair, I cannot destroy a pair. That is the most natural reaction. If you understood it, I am very happy for you, because I was 2 weeks trying to understand this when I first learned this. So pairs is now what I am looking at, okay? Great. Let's say this is process 1. Process 2. Yeah, anyone wants to do, if anyone wants to say something? Birth, one birth, yes. So let's say I have something like this. And now I go to here, no? Okay. Something like this? Yes? So if I write, and then the B, of course, no? If I write something like this, we all agree with the relationships that we learned in terms of densities of pairs? It's the same, right? We know that this is related to this. Very good intuition. But now I have something else, right? When this guy is going to be born, is going to reproduce, sorry, she can choose left or right. So it's over 2. And something else? Bruno? No? Something else? Yes. It's the same if it's plus 0 or 0 plus. Very important point. I told you I was going to do this in 1D, but tell you when things get different when you go to other dimensions.
So again, speed b over 2 because you can choose left or right.
Yes.
Another one choose appear.
Yes.
Times 2
because it can see the 0 plus 0 is the same as 0 plus.
can be a 0 on the middle and
Yes. These two here, the right left, when you generalize this to other topologies or to higher dimensions, this is the coordination number of the node, the number of neighbors that it has, right? So this is going to be cancel everything, but well, let's keep it like this. And what Bruno said is correct. I can use Q plus 0 and rho 0. I rewrote it in this notation because it's what I have here, and I don't want then when we do all the changes of variables. If I do it by hand without guiding, I will get lost and it will be a mess. But you can do what you did, and you can choose your variables, remember, okay? It was not incorrect, it was correct. Any other process? Sorry? Taking both of them down. We are one by one. We are one process by one process. But we are missing some, yes, non-intuitive.
Maybe there is like 2 zeros and with neighbors that reproduce.
Yes. Sorry, I thought it was some, yes. So let me, there is 2 zeros?
Yeah, 2 empty and another plus.
Yes. So basically, I think what you are saying is I have this pair, and I go to this because I had a plus here that moved from away.
No, yeah. Yeah, I was thinking about a pair of 0, 0 with a plus in both sides. And then both can...
0, 0, and then a plus.
And the other side a plus.
And another side a plus.
Yeah.
And then what will happen?
Both plus could...
Only one. I can only change one sign here.
Okay, okay.
What happens? This?
Yeah, this can happen.
Okay, and did I write something here that is the same as this?
Yes.
Perfect. Great. But it's important. It's important to think of all the options and then see. It's this one, eh? Sorry. Well, I don't know. I mean, after so many plus zeros, maybe. Great. We are almost there. This is the last bit. I'm going to require your attention. Then it's all algebra, okay? So keep the coffee that you ate and the sugar that you drink active. So basically, this is the process. I have a plus, and I have this same pair, but now I have a reproduction from this side. And this is the term that is tricky. So basically, the probability of this is the probability that I take again at 0 plus, duplet, and now comes the problem. The problem is that now my conditional probability is the probability that I chose the duplet, is the probability that I choose a plus conditional to having chosen a duplet here. So basically the probability that I chose these 2 guys here, and then I have a plus next to them. And this is the important, this is the tricky point because of this. Because this is higher order correlations now. This is the important point. If you didn't follow the commutation, the counting, you can try again and again, or you cannot even try it if you never need it. But what it is really important for all the discussions that we're going to have to build intuition and to understand all the systems that we're going to discuss, forget about the math, is that you understand this point here, that you understand that when I write this second moment, I get it with higher order correlations, longer range correlations. And then of course here I'm also missing, well, this is B, and I am missing a lot of factors that are not going to fit here. Okay, something like this.
Should it be divided by 2?
Yeah, those are the factors that I missed. Yeah, and many more. Divided by 2, by C, I agree. I have the symmetry from here. Yes, something else? Yes? What else? You don't know, but something else, because if not, I don't need so much space. Yes, exactly. Anyone that is not this guy here in 1D is trivial. Imagine that I am in 2D. I don't care about this, right? Okay. I am looking at updates of this place because of the neighbors, right? So in principle, everyone that is connected to this guy, sorry, this is a 0, eh? Everyone that is connected to this guy, but it is not in the initial duplet that I took, can invade this place. So this term has to be multiplied by C minus 1. Sorry? For 1D, this is a 1, right? So I'm not going to use it. So, sorry? So, important, don't give up. If you didn't follow all the counting, you can repeat it. You won't follow it maybe, you can repeat it and you can get used to it. In the books that I explained you, that I gave you, sorry, in the drive, you have the links, you don't have the PDFs. There is the calculation is done there with the same variables that I did here and with different variables. You can try both if you are interested and see which one is more accessible to you and which one adapts better for you. But again, the important thing I want you to understand is that all I'm doing is I am writing, I have my equation in terms of an additional variable, and I have to write an equation for the new variable here. And now, of course, now I have a lot of problems that I need to solve, but that's where I am. The problems that I have are many. The first one is that here I have rho plus 0, and rho plus plus is okay. And then I have this additional problem here. So I have two different problems with two different solutions. The first problem that I'm going to attack is this one. And then we will see how we handle this one. But I guess this one is clear for you, how can we handle that, right? It's just the density of doublets is correlated. Sorry, I don't know if it's doublets or duplets in English anyway. None of us speaks English. So, pairs. I can write it in terms of the one that I want. Or I can even write this in terms of the one that I mean, it's the same, okay? But this is the one that has physics or intuition behind. Yes, Miguel, microphone.
I just got a little bit lost. The times 2 and over 2s, they're 2s because we are in one dimension.
Yes.
And then you suddenly put a term in the end that's zeta minus 1 that scales according to the dimension we're in.
Yeah, so all this is depending on the dimension. This is, in reality, is C.
Oh, okay.
Because this is given that this plus is going to, given that a plus is going to reproduce, it can go to one of the neighbors, right?
Okay, okay.
And C minus 1 is this example that I built, that any connected to it can invade it there. Great. So I am not going to do the algebra of rewriting rho plus 0 in terms of rho plus plus. I'm going just to show you the result. But I am going to write the approximation that is the important thing that we want. So basically what I have now is this local probability here, no? How would you approximate it? What would you put there? This? This? Rho? This? Ah. So what is this probability telling me? This is the probability that I take a plus 0 first. So this is the, sorry, I always read conditional probabilities the wrong way. This is the probability that I take a plus conditional to this choice before. And when we were doing the well mixed, we were saying that this q plus 0 was the probability that I take a plus conditional to having taken a 0 before. And what we said is, well, I don't care. I just want to care about the rho plus. This is what I want to do. And I don't care about the neighbors. The square of the q plus 0. Okay, there is something that we are doing now that is not, I don't like saying it's not right, but they say it's not the optimal way of understanding this. Why are you saying all these expressions? What is guiding you when you say rho plus plus, rho?
I mean, if you look on the equation.
No, I don't want you to look at the equation. I want to look you at here. So what I want to do is I want to truncate correlations in a space. So when I was doing this, I was saying, I'm just going to look at the probability of taking a plus, and I don't care about the probability of the neighbors. I am stopping my correlations at the 0 order. If I want to go to the next step,
you have the probability of the 0 plus pair, which is rho 0 plus, times the condition probability. Wait, no. I'm looking at the equation, sorry.
so all I'm going to do is, if here I was caring about the probability of taking a plus without looking at the first neighbor, what I'm going to do now to extend and capture at least some spatial correlations is I'm going to look at the probability of taking my plus just conditional on the nearest neighbor. And I'm going to forget about higher order clusters. That is what I'm going to do. This is the reasoning I want to follow. And how do I write that mathematically? I write it mathematically this way. Okay? But the important thing, what I want you to understand, is the reason why I'm doing that, right? The reason why I'm doing that is because as long as in the mean field case, I was only looking at the focal individual, now I am extending my description one place, only one. So I don't care about the guy that is farther from my chosen place. And now, of course, I can write this, and this is another exercise for you to do, using the same reasoning we did in the beginning as rho plus 0 divided by rho 0. And this is the pair approximation, okay? So now I can put this here, and I have all my equations written in terms of, well, of course, rho plus rho 0 we know is 1 minus rho plus, and then you can rewrite rho plus 0 in terms of rho plus plus and rho plus. You can do it, it's algebra. And if you want my notes copied, it's done there, but I don't want to do it because I'm being a bit slow. Great. So keeping the notation in case you want to take a look at this. At the end, I get an equation for rho plus. And this is the equation that I get for rho plus plus. So this is the system of equations that I get. What I was saying in the beginning is that sometimes what you will see, and in one of the books you will see that they do that, they arrive to here, to this pair of equations, and because we discussed that yesterday with Ian's group, they are interested in looking at the local probabilities, how they change in time, the Q++. Basically what they do is they say, well, now I know Q++ is equal to, I always do this wrong. I have to do it this way, because if not, I get lost. So Q++ is equal to rho plus plus divided by rho. And they apply the chain rule here. And they basically transform this into an equation for Q++, and then they work with that. It's the same. It depends on the information that you want to get, okay? It's the same. Chain rule. I don't know. I always work with this, and I want you to, on Friday, I'm going to give you a paper in case you want to learn about this that uses these variables. That's why I'm following. Okay, so we have this system of equations. What do you do? Solve it. Yeah, you start to know me. How do you solve it?
Null lines?
Null lines, yes. But here with the null lines, there is something very interesting, which is that I also get information on how the doublets go, no? So I also get information about correlations. And if I write my equations for Q++, I do get an expression of how the local probabilities change as the global probabilities change. That's information I didn't have before, of course. Makes total sense. There is also something that you have to be careful when you analyze this system in a phase space and you do this kind of analysis. And that's why I wanted yesterday to go back to it when we did it, remember, for the simple system of the two bacteria. Is that I think it's the intuition is clear. If rho plus and rho plus plus, they are, I mean, your phase space is not from 0 to infinity and infinity to 0, right? So the number of pairs that you can have is bounded by rho plus. So you need to be careful with that. We are going to try to save a bit of time. You can do this. You can integrate it numerically. You can play with the parameter, and you can try to get nice intuition on how this two-dimensional dynamical system changes. What I'm going to do is calculate the fixed points directly. So I'm just going to equate this to 0, and instead of calculating the null lines and looking at how they fix, I'm going to solve this system. And I'm not going to do that, of course, because that would be spending a lot of time. So basically, we have one fixed point that will be 0, 0, and we have another fixed point that is b minus 2, b minus 1, b minus 2 divided by b. And I am going to rewrite this 1, 2, b minus 1, 1 minus b minus 1, and 1 minus 2 b minus 1. Exactly. Yes. The only reason why I'm doing this is because if you remember yesterday, we were drawing everything in terms of b minus 1, and I'm going to show you the results. Fixed points. I think it's hard from the back to see this. B minus 2, B minus 1, B minus 2 divided by B, and just dividing by B on both sides, 1, 2, B minus 1, divided by 1, B minus 1, 1 minus 2, B minus 1. Well, it's the same. Good. So now, we go back to the comparison of the results that we had. We had numerical simulations for the red dots in one dimension. We had the black line in mean field, well, mixed case. And of course, we can plot our fixed point. Sorry, maybe this is a bit confusing. This is for rho plus plus, and this is for rho plus. No, the other way around. So if I plot that, I want to keep the mystery. What you see is that now I get a much better approximation. As we expected, the approximation is worse close to the critical point because correlations are higher, are longer range. So then my approximation has to work worse there. But you see that I already see a significant quantitative improvement in my approximation. And remember that we were saying yesterday that in this case, my model is so simple that all I see is a quantitative improvement. But if the model is more complicated and space, so here the only thing that the space is doing here is deciding to which point I can fill my box. Because there's nothing else I'm doing. I'm just filling my system with a percolation process, right, with a replication process. But if I have more complicated dynamics, maybe this space is responsible for those dynamics, and this better approximation captures space better. And that's what I want to, sorry, I don't know why now we are going to have, I think I got very happy when I got this result and I did like 4 slides identical. Anyway. Perfect. So now what I want to do, we are done with chalk for today. We have 40 minutes. And I want to go back to the bacteria case that we saw the first day. And I want to give you an idea of how different and how complicated things get and how much understanding of a biological system we can get when we get the complicated path, okay? I'm going to show you things that are, like long equations that have a lot of algebra behind it. In the paper, it's all done. They have a lot of appendices showing how you do this. If you want to have some fun, you can do that. I'm not going to do that. But if you are curious, it might be a good exercise. So if we go back to the bacteria case, let's see if I have here an example. No? Well, maybe I can, then I have to rewrite the model. So remember that in the bacteria case, we had 3 states, no? We had one, toxin producers, toxin non-producers, or toxin sensitive, and empty. So we had a mess. We had 3 global variables with their constraint. And how many local densities I had? I had Q plus 0, Q plus Q, Q 0, 0, Q 1, 2, 0. And I had the same change in this here, no? So I had 9. Local probabilities. I have 9 variables here, and I have 3 variables here. Remember that if I talk in terms of doublets, it's the same because the doublets are related to the others. I have 12 variables. You can do the exercise at home, or you can read the paper. I have 7 constraints between these variables, just taking into account the connections between local density, local probabilities, how they equal to 1, and this global constraint. So if I have 12 variables and I have 7 constraints, I can write the dynamics of my system in base of 5 independent variables, right? So what for the case of the contact process was a 2-dimensional dynamical system, now it's a 5-dimensional dynamical system. That makes sense because the mean field was already 2, so it makes sense that it scales, no? Yesterday in the groups we were discussing whether we wanted to have death in our model that we were building or not. Those that were in the ecology project, those that were not, we were basically building a model very similar to the one that we have for bacteria. And we were discussing whether we wanted to have 0 states or just 1 and 2 and allow them to move. if I introduce depth, and if I introduce the zero state, I have more variables. So that's why I was telling you, when you want to do the theory, you really appreciate being able to get rid of the zero and substituting that by replacement. And this afternoon and tomorrow you will realize and you will be happy that we did that. Great, so these are my five equations in the screen. These are the same that they chose in the paper. They chose to use row 2 and row 1, that makes sense. Row 0 is boring. And they chose to write with Q11, Q22, and Q21. This is usually a common choice because it gives you kind of the probabilities of having identical neighbors, like common specific neighbors, and one of the interspecific neighbors. So it gives an idea of a spatial structure more straightforward. But in the paper, if you read it, at some point they want to calculate something else, and they say, to calculate this, it is more convenient to work with these variables, and then they redo one of the change of variables, and they work with another Q, and then they calculate what they want. So you can go back and forth depending on what you want to study. Remember, this is this 1998 paper with the simulation and the space. Great. So now I think, what would you be interested in looking at when you have this refined system? Remember that we had for the mean field case, I don't know if you remember, but let's remember that. We had this kind of picture, right? Remember that we had for high production cost, remember that the cost was the difference in the reproduction rate of the producers and non-producers. If this cost is very high, the system is monostable and the non-producers always win. That makes sense. I'm investing a lot of energy. Remember that? If the killing behavior was not very effective, this gamma parameter was small, the system was still stable here. But then I had a whole region in which my system was bistable. You remember this? This kind of plots that we were saying that basically if I was starting my initial populations here with, let's say, 0,2 producers and 0,2 non-producers, the producers will win. But if I started with a high density of producers, they will outcompete the non-producers. And this was biologically a bit weird because we were saying that having this threshold density for the invasion of the producers was not very useful in terms of understanding how this population could invade a given environment. Do you remember that? Okay. Then when we were doing spatial simulations, the picture was different, and we were seeing that this threshold was disappearing, and in simulations in the lattice, the population of producers was able to grow and outcompete the non-producers. So the biostability was kind of disappearing for the same parameters where I was finding biostability before. And the question was, how does space capture that? So what these people did in this paper, once they come up with this system of equations that captures spatial correlations, short-range spatial correlations, they try to reconstruct the phase diagram that I was showing you before. So basically they were saying, well, if with mean field, with a well-mixed approximation, I get this kind of phase diagram, bistability and monostability, what do I get when I introduce space? What is the phase diagram that this per approximation gives me? And this is what they found. What they found is that the biostability region remains on a much narrower region of the phase diagram, but now there is a very big region of the phase diagram that actually, if you think about it, it makes sense, that is for high effectiveness and low costs, in which the producers are able to dominate regardless of their initial condition. This is very important. In this region, I have monostability. The dominance of the producers is monostable. I don't have the threshold. I recover the numerical simulations. I keep the biostability, I still have S, the monostability of the non-producers there. Remember, the fact that a behavior is in the model, it doesn't mean that we not have to find it in the experiment. We were already discussing that this region was biologically not very meaningful, and there may be arguments to think about whether, I don't know, maybe this region is here and it's just the parameters of the experiment are not there. Okay? So don't be never bother if you don't get for any parameter combination the behavior that you're looking for. So this is nice, this is good. We can reinforce that picture looking at this other diagram that we were constructing, or they were constructing, in which they were looking at the behavior of this threshold. Remember the threshold in the producer initial population as a function of the cost. And they were saying, well, when the cost is higher, this threshold increases, and there is a critical cost above which I lose the biostability. There is a critical cost above which I lose the biostability, and non-producers always win. So it's only for small costs that I have this biostable regime. I can do this with the mean with the per approximation. And as you can see now, I get a very similar phase diagram, but what is taking your attention? What do you find interesting here in this plot? Sorry again, there is?
The curve doesn't start at 0, 0 point.
Yes. So there is a region. There is a cross threshold for, there is a second cost threshold, right? There is a cost threshold for monostability. So basically, this is the key difference. Here, the threshold was hitting 0 for cost 0, and now it hits 0 for a cost larger than 0. So that means that for a small cost, there is still possibility of the producers to grow from a very, very small population. What is very interesting about this paper, and I am not going to go into that because this is not simple calculation, but they are even able to calculate the conditions for this invasion to happen depending on the rates and depending on the initial structure. So they do a lot of calculation. These guys, Iwasa and I think the other author is Nakamura and Simon Levin, they know what they do. So they calculate a lot of things, and most of the calculations they do, it's not only that they are long and you say, wow, what a big calculation, but they are also very creative in the beginning, no? And I think that's something that is, I like a lot. I like more than, I don't know, when I see a lot of pages of calculations and I say, wow, and I didn't make any mistake. But when you see how they propose that calculation, no? How they find that they can calculate things from the equations, that is, to me, is really, really, really interesting. And they were able to get many things. So, questions up to here? No questions? So if I give you 30 minutes, you are able to calculate the per correlation for the per approximation for another model? I am almost done, but yesterday we had a discussion in the project session that I thought was very interesting, and I added a few things to try to get deeper into this idea of the per approximation and try to see if I am able to build a clearer picture of what is the core of the approximation. So yesterday we were discussing about the differences between this, yes?
Just about what we were talking before. Would you please elaborate on what's the difference between the P and B phases?
What is the difference between them?
The P and B phases. I mean, they are similar somehow, but how to make the physical distinction between both of them?
Well, in one case, the system is bistable, and in the other case, is monostable. P and B?
Yeah.
Yes. So on the left, I only have B and S regions. That means that I only have the non-producers winning, or the producers winning or losing depending on their initial density.
Okay.
Here I have the same two phases, and I have the P phase in which the producers win regardless of their initial condition.
Oh, I see.
So basically, the P and the S are equivalent, with the only difference of who is the winner. Whereas in the B, one or the other wins depending on where you start. Okay?
Yeah, I see.
Those curves meet at some point. Like
I don't in the paper they don't show it, and actually maybe you can get it from the expressions that I give, but
after that, is there a bistable state or not?
that's a good question. If at very high effectiveness you get a bistable? I mean, I don't know. Should you? Yeah.
There is no bistable one.
Maybe you just lose them. I think.
It is intuitive that you just lose them.
Yes, depending on how far we get into the project, you will see something very similar. And if not, I will give you a paper where I'm not going to say that the authors of that paper were smarter than this, because then it will be risky, but you will see how you can lose this in if you're familiar with bifurcation theory, basically that's what may happen, no? That you may lose biostability via bifurcation, and I guess that should be the case, no? When you
This makes sense. It's confirming the question.
yeah.
My last question is, these plots that we are seeing, are they from simulations given a certain rule, or they are the solutions of the equations we saw with some approximations?
So this equation here,
Did you get my question?
yeah.
Okay.
So this plot here is basically the solution of the mean field equation. You can calculate the conditions for the existence of this saddle node, this fixed point in the middle, you remember? When the null lines cross, and depending on the, when you get the conditions for the existence of that fixed point, that gives you this line. The transition between the two regions. So that is from the theory. What they do here, the way they construct this here is way more creative. They look at, they manipulate the 5-dimensional system, and they start creating initial conditions and try to look when the producers can invade or not a given population of non-producers, and when the conditions for invasion depend on the initial condition, they define biostability. But none of this is using numerical simulations of the lattice. All of this is analyzing the system of differential equations. Of course, when you have a very long linear system of differential equations, at some point you have to use numerical calculations to find the fixed points or whatever. I think they don't do that in this paper. If I remember it right, they create these scenarios in which, for instance, they say, well, now I want to see if the producers can grow. So they say, I am going to create an initial condition for my dynamical system such that rho 1 is going to be 0, because I don't have any. Rho 2 is going to be in the stationary state. And Q1 is not going to be 0, because even though I have a small number of organisms, they will be very close to each other, and then the local probability will not be 0, right? So if you have 2, and that is when things get a bit more counterintuitive. If you have 1,000,000 cells, and you have let's see how much I was able to explain you. I have a very big lattice, and I have 0, 0, 0, 0, 0, 0, plus, 0, 0, 0, 0, 0. And I have a lot of zeros until n equal to 100. Who can tell me rho plus? Don't be shy. I mean, at this point, it's fine.
2 over 100.
2 over 100. Who can tell me Q plus conditional to plus? Sorry?
1 over 100 times 99. Like 99 is the denominator. But you can choose which pair, and there's only one pair where there's a plus 90%.
A half? Wow, that's a very, very counter current answer. 1/2. Who thinks it's something like this? Just orders of magnitude. Who thinks it's a small number like this? A big number like this? No idea? Okay. This afternoon, tomorrow you have to tell me which is the answer. I'm not going to tell you the answer. Because this is the whole thing of the course. I'm not going to spoil myself. Use the relationships. Move around and try to find one that makes you, if you are able to answer this with understanding.
I think it's 1.
I don't
Because
know.
it's
One.
rho
We have
plus,
more of,
it's rho plus plus divided by rho plus, right? Rho plus plus is 2 over 50 because there are 100.
tomorrow you tell me the answer.
Yeah.
Now I want the rest of the people to think.
Let's try to elaborate.
We have 3 options. We have a small number, we have 1/2, we have 1, which is a more extreme answer. The only thing I'm going to tell you is a number between 0 and 1. And it's real, so you have one option for each of you, or more than 1. Good. Sorry, now I lost. Why did we start talking about this? What was the question that took me to this? It was some of your questions.
I asked.
True.
I asked if the simulations they were done was with specific conditions for the lattice, or they are or if they are just solving the differential equations.
Yes, and my
with some
answer was it was
approximations.
based on the differential equations, but for this specific system, the way they handle it is to calculating invasion conditions. So assuming a very specific initial condition and looking how this population was able to grow, and then they assume that rho 1 is 0, rho 2 is in the stationary state, and then is what I was saying, that the fact that rho 1 was 0 doesn't mean that Q11 is small, and then they get the calculations. Nothing is with lattices, okay, with a lattice simulation. What is with a lattice simulation is the last bit I want to show you, which is, let's see if we can see it in the screen, because now we are facing the problems of technology. Yeah, we cannot see it. This is a problem. I tried to color this, but I don't know how to do this. This is supposed to be the spatial simulation in their grid. And this is an initial condition where they have empty places that are white. They have producing places that are black. And they have non-producers that are gray. The problem is that it seems that the gray and black are not very clear, easy to distinguish. Maybe in the paper it's easier, let's see. Because I really want you to see the idea. Is this the paper? No, this is another one. No. Okay, well, anyway, you will trust me. And you will go to the drive. I promise I tried to paint it with paint, with GIMP, with all I know, but anyway, what they see, nah, it's impossible. What they see in the simulation basically is that you start with a random pattern. If you open the PDF in your computers and you zoom in, you will see it. And then it's great that now we have colors, no, and everything. And then as the dynamics go, what they see is that this random pattern starts having some order. So the black clusters start growing larger, and the gray clusters start growing larger as well. And at some point, the black clusters invade the gray ones. Right? That's what they see. And then here, all they have is black, that remember represents producers, and empty spaces, representing a full invasion of the producers in the system. The initial condition that they take, I think, is 2080, which means very, very few producers. Well, not so few, but not so many. And they see how it invades. And the reason why I wanted to bring this idea is because they do a final analysis, and I think this one is based on simulations, in which they run a Monte Carlo simulation of the model and they calculate the local probabilities. They calculate the Q12, that is the probability of taking a 1 place conditional to a first choice of a 2, remember? And then they calculate the higher order correlations that they are neglecting when they do the pair approximation to see how good their approximation is. Remember that what we are doing when we do this Q12, when we do the pair approximation, what we are saying is that this Q12 is equal to these two probabilities here. And what they see is that it is not. I mean, well, if for one of the cases it is, so the dots are equal to the down triangles, more or less, but you see that the Q21 is much larger. What does it mean? What is the meaning of this result? And sorry, maybe it helps you elaborating your answer. They do the same for 1, 0, and they get also very different results. Anyone else? What is the meaning of this probability? The probability that I take a 1, given that I take a 2, 1, is much higher than the probability of taking a 1 given that I took a 2. The ones.
Which ones are the producers?
The producers are the ones, and the non-producers are the 2.
The ones are more likely to surround the twos, like that.
The ones are more likely to surround the 2s.
I think is that this process happens more often than the other ones.
The process happens more often than the other ones. Lauro, what was your answer?
I would guess that there's a correlation in the system.
There's, yes, but what is the meaning of?
In terms of equation, we should go to third order, right?
Well, yeah, of course. The fact that the Q12 doesn't agree with the Q121 and the Q122, that means that my approximation is not ideal, no? I'm saying that they are approximated and they are like, I don't know, sometimes, I don't know, a factor 2 or 3.
Maybe they are separated.
They are separated, why?
I mean, one region is more ones and another.
Yeah, but why are you getting to that conclusion looking at these plots?
Yeah.
Because that answer, I buy it, but I show you the simulation. How are you interpreting these probabilities in terms to get there? That is what I want to know.
That's it. Maybe building on what my colleague said, given a Q1 to find another one close to it, then we should have kind of maybe a cluster of twos with the one on the edge, the way that this separation would be defined, right?
Almost. But you need to look it from much broader. Don't look at the interfaces. All I'm telling you, what I'm telling you now here is, to all of you, is when I choose the probability that I take a 1, right? Conditional to having taken a 2, 2, so the probability that I have a pair of 2s and then a 1 next to it is much smaller, the blue triangles here, is much smaller than the probability that I take a 1, 2, that I take a 1 after having taken a 2, 1. So it's much more unlikely that I will take a 1 next to 2 2s than taking a 1 next to 1, 1 and 1, 2. And what that is, and you can interpret that same result in terms of this plot here, even maybe bigger. The probability that that basically what this is telling me is the probability that ones are close to ones is much bigger than the probabilities that 1 are close to 2. Because they grow in clusters. Because they grow in clusters, my local probabilities are very big. And when I calculate the pair approximation, it's a very bad approximation, especially for empty interfaces with bacteria. Why? There is no lunch until someone tells me why. And I have the key. Yes. My question is, let's forget about this plot. I think this plot on the left may be more confusing because there is a lot of points there very close to each other. Let's look at the one on the right. The one on the right is the one I want to study. I'm showing you the probability that ones are close to 0 twos. And we are seeing that that probability is much smaller than the probabilities that ones are close to 0 ones. We all agree, and we say, well, that means clustering. Now we are saying, when I calculate the probability that ones are close to zeros, that is a very bad approximation for these two probabilities that I calculated before. So my question is, why, especially at short times, when I approximate the probability of ones being close to pairs of 0 ones by the probability of ones being close to zeros, why is such a bad approximation? The clusters are not well formed yet? Sorry, Ben? Exactly. Actually, it's the other way. In this region here is where I have more clusters. Here I don't have clusters. Here I have dominance, no? And that's why they match. The reason why here the crosses and the circles are identical is because now I only have ones. Well, not only, but I have a lot of ones already growing a lot. But here, when I have a growing correlation length, a growing clustering process, is exactly that. The pair approximation is not taking into consideration the clustering. The pair approximation, what it's telling me, is the probability that I have a 1 next to a 0 is the same everywhere. It's the same everywhere regardless of where I have next to them. So as much as the well-mixed approximation is telling me that the probability that I take a 1 is the same everywhere in my space, the pair approximation is telling me that the probability that I take a 1, conditional to having chosen a 0 next to her, is the same everywhere in the space. The idea of the pair approximation is the same as the idea of the well-mixed case. It's just that now we are talking about pairs. We are not talking about focal nodes. Okay? Maybe, I mean, I understand interpreting these plots is not very intuitive. That's why I wanted to discuss them with you the first time. I mean, it really depends on what you like doing and the kind of things that are interesting for you. If you don't find these kind of ideas extremely interesting, I think it's okay, just with the intuition that hopefully you got in these 3 classes. If you are interested in these things, I recommend you a lot to read these 3 papers that I put in the drive. They are very well written, they are short, they present the experiment, they give intuition about the experimental results, and then they produce a model, they do a well-mixed limit. They were not able to, well, I know they were because I know the people that wrote it, but probably they didn't do it at that time. And they say, we do simulations and this is what we find. And then a couple of years after, they come back and they refine the approximation and they show the new results. So I think it's a very good story in terms of how they got to the point where they got with this system. And I recommend you to read all of them. Just to finish, and now I swear I'm finishing, if you are interested in this saga of results, there is another paper that it's also in the drive, in which they also study this same system, but they model explicitly the toxin, kind of. Remember that we were saying that in the beginning? And that is very interesting because what they show in that paper, and those of you that are working in the ecology project, maybe that clicks something on you. What they are showing there, because something that is very, I don't know if limiting, but we don't have coexistence of the two strains here, right? So in that fourth paper, what they do is they try to model the toxin, and they show that basically when you account for the actual dynamics of the toxin, when you create these exclusion areas, remember these exclusion areas here, the first cells that will go back to it are the ones that grow faster, the ones that don't produce. So they will invade because they are better competitors filling the space. But then there is another shock of toxins that kills them, and they clear the space again, and they are replaced, and they are continuously being invading and being replaced, invading and being replaced, and that keeps both of them coexisting in the system. So there is a kind of